And then after you've basically gotten the audio out of the RF, the low frequency out of the high frequency component, you amplify again. So you can actually drive a speaker, which requires more power than the radio signal coming off the ear would be able to give you. That's a basic building block. But there's fancier ways to do it too. This circuit right here is the old-fashioned way. They have another, a guy by the name of Edward Howard Armstrong came across the concept of, you know, if I have to do this, I also have to do it here. And I have to do it at every stage. Why can't I just, instead of having to vary all these things synchronously, why can't I just find a way to convert what's coming into a known frequency called an intermediate frequency, and then everything here can be carefully tuned to that intermediate frequency. And they do that by mixing what comes in with the local oscillator and producing a third frequency and actually a fourth frequency, but you only pick one of them. The process is called heterodyning. In modern radios, you have what's called a super heterodyne circuit, and it's called super because you take the upper of the two heterodyne frequencies that result, and you block out the other one. With the few minutes that are left, I'm going to go back just a tiny bit, because this will become important as we go along, and pick up on something I didn't talk about last week, and I probably should have. But it's essential to understanding a little bit more about filters and this signal processing. It kind of occurred to me that, yeah, I got to cover this. The concept I'm going to talk about is called time constant. And it's going to sound like the first episode you had here where Craig talked about maybe he didn't, could have talked about a capacitor. And that capacitor gets turned on, and I talked about this. There's your voltage. You turn it on, the charges start to show up here after the switch is closed. And what happens is you go from 0 voltage to, this is 10 volts, this eventually becomes 10 volts, remember? Everything in the loop has to add up to 0. So here's the voltage used in the charge, and basically this curve will get there. The question is, how long does it take to get there? I can't give you an exact answer because this is an asymptote, meaning it really, in pure technical terms, it kind of, approaches it. It looks like it gets there in a split second, but it's really getting there, and then the closer it gets, the slower it approaches, and slower and slower. The word asymptotical approach is really the correct way to describe it. So there's an easier way to measure on the time axis. This is the voltage you get. How long does it take to reach this particular point? What is that particular point anyway? Well, realistically, you need one of these as well as one of these in the circuit. Why? Because the minute you turn this on, you got a short circuit. You really need someplace for the voltage in the loop to go. So basically, as this thing gets charged up, the current tapers off, and when the current tapers off, the voltage here goes down, the voltage here goes up, and they kind of trade off. Remember, the voltage has to get two voltages added together have to equal this. So as this gets charged and goes up in voltage, this thing will go down in voltage because the current going through it is going down. And the time it takes is actually a function of this resistance in ohms, and that capacitance in farads, and that's called T, or tau, the Greek letter tau, and it equals R times C. And how long would it really take it to reach this magical point? Let's just, for the sake of measurements, say we have a 10,000 ohm resistor, and let's say we have a 10 microfarad capacitor. Okay, R is 10,000, or 10 to the fourth. 10 1,000 is 4 zeros. 4 zeros is the fourth power of 10. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. 4 multiplications, fourth power. Micro, that means millions. So it's 10 to the minus 6, but I'm going to have 10 of that, so it's really one less. So here we have 10 to the minus 4 times 10 to the minus 5th. When you multiply these together, all you have to do is add the exponents, and you get 10 to the minus 1. And it happens to be 1/10 of a second. That's how long a 10,000 ohm resistor and a 10 microfarad capacitor would take to charge up. 1/10 of a second. That's not very long. This thing's not that small of a capacitor, not that big. And that's, you know, pretty medium-high resistance, but that's pretty much the values you have to deal with. If you want a long time period, you're going to have to use very large capacitors, very large resistors, and you can do that. But maybe you don't want to. It depends on what you're trying to do. And you'll see when we get into modulation, especially demodulation, we have a thing called an envelope detector where this becomes important. Now, what's this magical time period here? The time period, you're not going to believe me when I tell you this, is where this becomes about 63.5%, or let's just say 63% charged. And if this is a decay curve, this is where it's 37% decayed. Where in the heck did that number come from? I'll give you the answer. You don't have to take my word for it, but it's the answer. This is a differential equation. The thing charges up according to how much voltage is there. It's dV dt, the voltage change over time is equal to the amount of time. So as time goes further along the voltage, you're going to get this change. And anybody who took differential equations in college knows that when you try to find an arithmetic expression that will satisfy that, it comes out as an exponential. So it's the value of e to the x or minus x, and if it's a decay. And that means this is actually the point where you grow to, you decay to 1 over e, or it's 1 minus 1 over e in this case. Now what is e? It's the base of all natural logarithms. It's 1 over 7. 1 over, and it's 2.718. If you go 1 over that, that's where you get your 37%. If you subtract that from 1, that's where you get your 63%. That's where it comes from. I'm just handing you this. So the time constant is based on how long it takes to get to that magic percentage. Let me give you one more example because we're over time already. When nuclear material decays, they talk about half-lives. Why? It might take 400 years, or 400 million years rather, for uranium-238 to turn into lead by radioactive decay. But the thing is, the rate at which it decays keeps going down. The less radioactive material, the slower the decay. So they find it easy to say, given this math and differential equations, they can speak about when it goes to half of what it was as being a constant. So many years later, half the uranium is going to be there. An exactly equal amount of time later, half of that. An equal amount of time later, half of that. That's the same concept here. This is differential equations. So we found the point 1 over e, which is a point where we could compute it easily. Tau equals r times c. And in that time, you'll be at that percentage of decay or that percentage of maximum amount of charge up. This is the number you use to compute how much of a capacitor, how much of an inductor you need to make a tuned circuit cut off, what's the frequency where it stops conducting, is based on that time constant. We'll get into real detail on that, and at that point you're going to start really feeling the electronics and the radio parts of this course, and really feel like now I'm a ham operator and I understand something about why a radio works the way it does, and why when I turn the knob things happen the way they do. And it's going to get more and more interesting as we go along, because from now on we're talking radio. And let me think, are we meeting next week? I hope so. Yeah, 29th is our meet date. Week after that, I'm in France. Oh, no, actually the week after this is the 5th. So we're gonna meet next week and the week after. It's the week after that I'm gonna be traveling again. But the good news is in 2 more weeks, I'm gonna cover just about the rest of the course. And what I'm gonna try to do in the remaining couple of sessions is to do problems and answer questions and maybe go over material. Cover a couple of special things like binary numbers and logic devices, because if you're going for a general or especially an extra class license, you're going to see logic gates called AND gates, OR gates, NOR gates, NAND gates that make computers work. And that stuff is on the test if you go for an extra class license, or will be if you eventually want to take that license, and you should. And other things that we could cover that are what I call special topics. And I hope you're going to start reading that book and question poll and bring a lot of questions, because I can't believe you understand it all, but you probably will understand more after having gone through this process first.
I have a question.
Go.
What's your favorite thing to do with ham radio?
DX. I think the coolest thing is to be able to say, sitting at the table, you're talking to some guy. Let me give you a cute little example of this. When I put my current rig on the air back in 1980, I had one when I was a teenager that I built. But then when I got back into the hobby, I bought a Drake TR7, which was purchased because it's all solid state, covers all the frequencies from 0 to 30 megahertz. It's all solid state, so I can run it on 12 volts, so you can go mobile or base station with it. And I did, such a hurry to put it on the air that I took an antenna that a next door neighbor got rid of. That's a vertical trap antenna designed to go vertically instead of horizontally. It's got traps so you can run it on different bands. It electrically shortens itself when you go up in higher frequencies. And I struck it in the crawl space of our house in Deerfield. And to simulate the part about being in the ground, I took a piece of aluminum wire, ran it to the wall to a cold water pipe in the basement. And that's got to be about as inefficient antenna as you can get. So I started out with my first contact and I got somebody in the Zurich. My wife's rolling on the floor laughing, saying, "Oh boy, you are getting out there all the way to Lake Zurich. That's all the way down Route 22. Here, it's random. Let's see what I get next." Okay, the next guy I contacted was in Mobile, Alabama. And she said, "Not bad, you got all the way down to the Gulf Coast. Hey, good for you, try it again." The next guy I got was...
How many watts were you running? Just curious.
Yeah, well, here's the thing. I was on 20 meters. The next guy I got was in Rotorua, Tasmania, south and east of Australia. That's about as far to the other side of the planet as you could get. And then she said, "Okay, I'm a believer." And that is a cool experience, to be able to contact people in other parts of the world and really kind of get to know them. If you have a chance to talk to them for a period of time instead of in a contest, just making contact and saying, "Okay, next." I think that's the pièce de résistance, so to speak, of the hobby. Others see it differently. They love to experiment. They build digital circuits. They get into things called D-Star, which is a digitized kind of encryption process, encoding process really. It's not encryption. Some like Morse code because it's very simple, but it's a great way to reach very distant places because it's got the most penetrating power. It's got the narrowest bandwidth, so the amplifier gives you the most bang for the buck. That's what other people say. And they experiment with things like amateur television, the old fast scan, NTSC type of TV, where you can send your image. But nowadays it's easy to just send a PDF file using slow scan TV, which you can fit into an audio bandwidth. All this stuff is out there and all of it fascinates me. I think DX is the coolest part, but all these other special modes are, in their own way, great fun. And they'll all get talked about. I'll tell you how we deal with them. There's VHF, UHF. People that start out in this hobby usually go into start out with an entry-level license for technicians, which lets you do anything you want as long as it's above 50 megahertz. Not as much DX up there. You can do it through satellites. If conditions are right at 6 meters, you can reach out, but you don't get around the world very often. You mostly work local through repeaters, meaning high elevation transmitter and receiver getting together with one or more antennas so that whatever it receives, it immediately retransmits maybe 600 kilohertz further up the band like our repeater does on 2 meters. And then you talk to people you know, and meet at the club, and maybe meet for lunch sometime. There's something to be said for that. But HF is below 30 megahertz, especially when the sunspot is at its peak, and it's there right now. Is where you can take small amounts of power and talk to people way out there, 10,000 miles away. Try it, you'll like it.
It's fine.
And I'll see you in a week. Oh, and Rich's last name is Cull, right?
Yep.
Okay,
All day.
it's you?
Yes, ma'am.
Okay. Man from Indiana, mysterious one. I guess it's a good time to
Once your license, you can get your computer, take a phone, and